Hello, my name is Jack and I'll be your host for today. Welcome and thank you for taking part in MDPI's webinar entitled Novel Technologies for Energy Efficiency in Buildings. This is the third webinar in the Building series based on a special issue from our journal of the same name. If you're interested in contributing to this topic, don't hesitate to submit your research. Simply check the webinar's webpage for more information. I would like to remind everyone that the webinar today is being recorded and the recording will be made available as soon as possible on the webinar site forum page. Please note you'll have to be logged in order to view the recording. Certificates of attendance will be available shortly after the webinar to webinar attendees on their SciForum profile. To access yours, visit sciforum.net, create an account if you haven't already done so, and then simply log in and go to My Certificates. There will be two presentations today of 20 minutes each. The presentations are followed by a question time moderated by the chair. If you have any questions for us, please post them in the Q&A box at the bottom of the screen, and remember to mention the name of the person to whom you're addressing your question. Today's webinar is chaired by Dr. Alessandro Cannavale from the Polytechnic University of Bari, Italy. Dr. Cannavale is Assistant Professor of the Polytechnic University of Bari and is Adjunct Researcher at CRN Nanotech. He earned the qualification for Associate Professor in 2018. His research activity deals with applied thermodynamics and devices for energy efficiency, and he is an editorial board member of Energies, Buildings and Clean Technologies. Thank you, Alessandro, for chairing today's webinar. That's it from me. I'll now hand the microphone over to our chair. I hope you all enjoy.
Good morning, and thank you for your words and the journal Buildings for this precious opportunity. Moreover, I want to thank all the participants who have registered for this event. As chair of this webinar, I would like to welcome the valuable researchers for joining us today. As we all know, compelled by events, we must find new responses to the dramatic acceleration of climate change and the rapid depletion of fossil energy sources. Novel technologies may enhance the performance of buildings and reduce energy consumption. Today, we have two worldwide experts on novel technologies for buildings. Superinsulation, building integration of photovoltaics, and smart technologies for dynamic control of solar radiation are only a few topics of this webinar. Our speakers will share with us their recent advancements in relevant fields of investigation. Each speaker should complete the presentation within 20 minutes. Each contribution will be followed by 5 minutes of a short Q&A session for any question coming from the attendees of this webinar. Well, it's time to start our presentations with Professor Umberto Berardi, who is scheduled as the first speaker today. Professor Berardi is Canada Research Chair in Building Science, full professor and director of the BTOP Center at Toronto Metropolitan University in Canada, and full professor at Politecnico di Bari, Italy. Dr. Berardi has an extensive publication record, including 150 peer-reviewed journals, 130 international conference papers, and 5 books. His publications have received over 12,000 citations in Google Scholar, where he has an H index of 50. Dr. Berardi has a body of funded research comprising over $2.5 million in government and private sector sponsored research. Well, Professor Berardi, if you want, you can share your presentation with us, and the stage is yours.
Thanks, Alessandro. Thanks, Jack from MDPI, and thanks to all buildings community. More importantly, thanks to all the people that are joining this morning, or whatever actually is the time in your time zone. I thank actually Alessandro to have been thinking of me while organizing this seminar. And I really don't want to speak about nothing more than novel technology for energy efficiency in buildings. So the presentation is going to be, quite brief, but I hope actually can open up fields, question, interest, and a new thought at the end of the day. So let me give you a bit of the perspective that has often been happening while I was, moving to Toronto 10 years ago. I graduated in Bari And I moved to Toronto 10 years ago. And the reality is that although there is no animation coming up, and that's actually the first technical issue we are encountering this morning, the reality is that this is a 3D map of the city of Toronto. And if this animation was working, what actually would have been happening is that all these flat areas are now subject to major high-rise, skyrise construction. So in brief, currently there are 200 cranes happening in Toronto, and there are typically, on average, 300,000 new inhabitants in this city over the last 3 years. So what actually is happening? What this really testifies is the fact that this city, as many other cities, I'm thinking to Northeast, Southeast places, Singapore, Dubai, they are exploring a boom. They are exploring a significant request for more and more construction. And so, oh, yeah, you see, can you see actually the animation? Probably you see now. Anyway, the reality is that this city is exploring a huge boom. This is just an animation of 2014, but more and more towers are coming every day. And the reality is that there was a request to do things differently. We all realize buildings is a very conservative sector. We tend not to adopt a lot of innovation. When the innovation is disruptive and when the innovation is too advanced, people are skeptical because buildings are going to be there for 50 years and nobody wants to have any responsibility on failures of new technology. So when I moved to Toronto in 2013, I initiated this center thanks to a very generous grant from the government of Canada to initiate this group that was called Building Efficiency and later on Testing, Operation and Performance. And this is really what we've been doing over the last decade. So we have been doing new material development, but more importantly, we also have been doing testing in real field, a performance assessment of real buildings coming up and how those new technology in example cases can really behave in real field. So here is what I'm going to talk today. As you see, there are 5 different points of my presentation that you can follow 1, 2, 3, 4, 5 at the bottom right. And the reality is that I was asked to mainly focus on superinsulating materials, and in that field, my specialty is in hydrogen enhanced systems. But to give you a bit of an overview, I also have been taking the freedom to put a bit of slides on the possible values that phase change materials have in enhancing latent thermal energy storage in buildings, together with innovative foams. The point number 3, as another new categories of environmental friendly super insulating products. And then towards the end, very quickly and briefly, I'm going to speak about retroreflective materials and climate sensitive materials. So let's start together this journey. Now, you all understand that at the end of the day, building is supposedly to provide comfort for people. And in building codes, this is often pushing people to put more and more add value. Our insulation thickness becomes thicker with a lot of troubles. Our layers are becoming multiple layers with a lot of extra troubles. But the reality is that our value doesn't really always represent the solution to all the problems. And one of the problems that is becoming more and more important, especially in an era of climate change and hot waves and exceptionally higher temperature than what we were used to have. Think about Toronto. We used to have no air conditioning system 50 years ago in the entire city of Toronto. Right now, in the city of Toronto, for many buildings, office buildings in particular, the cooling demand overcomes the heating demand. So when these kind of things are happening, thermal mass and thermal storage are coming back as an important factor to reduce the fluctuation of temperature and, more importantly, to slow down the request of cooling power, which is becoming dominant in most of the countries around the world. Now, you can typically do thermal storage by using sensible storage. So you put massive buildings, massive construction, a castle, a church. You get there in the middle of the summer and it's extremely cold and nice and comfortable. But the reality, that's really not necessarily that much sustainable. It requires a lot of materials, a lot of mass movement that you need to do. And more importantly, it's hard to make skyscraper with massive construction because you need to actually go up in 200-300 meters from the ground with massive blocks. So the alternative way is by using latent energy storage. So latent thermal energy storage is a new frontier in new materials that is basically applying to the building sector, what we do typically when we put ice in a warm glass of water. So in principle, we are taking advantage of the fact that that mass of water, when it became ice, it was subtracted a lot of energy. And so when it gets into a warm water, kind of mug, at the end of the day, we'll grab a lot of that thermal energy back, it will melt, and then at the end of the day, you get a very cool glass of water. Now you can do these kind of things also in buildings and making sure that you get materials that are melting and solidifying. And because we don't like actually envelopes that are melting or are liquid, what we tend to do, we do encapsulation of a phase change material, so a material that can overcome a solid to liquid transition. But because we encapsulate those materials, we tend to do what we call a solid to solid thermal energy storage. Now, there has been a lot of research on PCMs. A lot of research has been often looking at these materials as a magic materials. But in my group, we find a lot of challenges with these materials. First of all, because selecting the right material is not straightforward. Researching innovative PCM that can be affordable, a low price is, challenging. And more importantly, because often people do a lot of research in a lab or in modeling, but then not that many research groups worldwide have invested time to do real effectiveness of thermal energy storage. Now, let's actually see this kind of three different research questions. Number one, there are a lot of PCMs around the world. There are so many that it's even hard to characterize them. There are, materials that are more toxic, materials that are, capable of store more energy, but in a temperature range that is hard to find in the building sector. So what we've been doing a lot of time is working with those materials that are often not necessarily the ones that really store a lot of energy, like the paraffines, but they can do that kind of storage in a temperature range that is close to building-related sector. Okay. Now this panoramic picture really gives you a bit of the bigger context of PCM. And this is, some of the materials you see my hand actually taking, a bit of this microencapsulated PCM. And encapsulation is clearly a significant factor in the value of these products. The reality is that polymer encapsulation is often challenging. It increases the cost quite a lot of the material. But on the other side, it provides you a ponder. And when you have a ponder of PCMs, you can introduce that ponder in any porous material by incorporation, immersion, mixing together. There are a lot of applications you can use that kind of ponder. Let me give you some example. In 2014, I worked with some students of mine, and we developed a PCM-enhanced concrete floor for a Stora Decathlon house. This house was full of glass, was gaining a lot of extra energy from the sun in the middle of the summer when the context was occurring. And at the end of the day, it will have required a lot of cooling power. And to mitigate the cooling power of this zero energy building, we ended putting PCMs in a concrete mix. They made the tile and the gypsum board of the entire house. There are a few publications I don't have time to go through, but basically we've been doing work on monitoring with and without the PCM, so getting away and putting back the tiles. We've been doing work in doing thermal characterization of this PCM, but also SEM picture just to understand if the polymer of the PCM was still staying as it is supposedly to stay, or the polymer could basically break for thermal related issues or mechanical mixing concrete related issues. That kind of work even evolved a few years later when we partnered with a company that does high-rise construction in Toronto, and we started partnering with them to put PCM enhanced wall board and gypsum board in some of the units. Now, the interesting thing of this latest research is that we were having, real buildings, real towers, and, in one floor, we were able to substitute a typical gypsum board with a micronal enhanced gypsum board, a product that is already in the market, although has been now, removed from the market, but really actually helped us understanding how the fluctuation was significantly slower and significantly more mitigated in the range of 6 degrees Celsius, and with a reduction of cooling energy demand by 15%. We have been doing work even on few other activity, and one of these is in-house that ThermoBuilt, a Toronto-based company, has developed based on a research idea that actually came from Europe, but found actually an interest in North America, where often precast concrete floor are quite common. And what we've been doing is basically, accumulating thermal energy in the concrete floor and then enhancing some of those kind of holes in a concrete structure, thanks to actually the inclusion of PCMs. And here you get actually one of the latest research we've been doing. We've been working on radon panels, where the radon panels is basically enhanced and surrounded with PCMs. So we aim to use this TABS system for cooling in offices, and mainly actually to provide cooling power more smoothly in different hours. So doing off-peak and promoting a bit of energy flexibility where the cooling can be on over the night, and basically the radon panel release that energy over the following day. And last but not least, we've been doing this kind of work with multiple PCMs and working on different PCMs. On one side, one interesting research area is to combine different PCMs to basically make sure that you can do thermal storage in summer and winter when the set point of internal temperature within a building could be slightly different. So, one material can have a set point of 20 and the other material on 25. And so you can address both cooling and heating season. The alternative is also to start looking at new innovative materials. Now, when it comes to new innovative materials, the challenge is often that we don't have actually a lot of new materials in PCMs that are being produced recently. But on the other side, a lot of these materials are expensive. So we had a funded project where we were working with companies that have organic waste from pork industry and animal oils that they wanted really to get ready. And we look at this as a new frontier of PCMs and thermal energy storage. And more recently, we've been working on also speeding up the process of charging and discharging of the PCMs, enhancing the structure of the PCM with new materials that have been generated and produced with a bit of graphene in the structure to make sure, like in your phone, you want the battery to basically be charging and discharging very quickly. Well, we do the same thing with thermal energy storage too. And here you get a bit of the sense of the work that my group has been doing over the last few years. Clearly, this is, a bit of the early stage, a bit of the chemical side, a bit actually you find in journals that are not necessarily the journal that we can expect building-related research, but I can guarantee the application of graphene nanocomposite will soon be applicable to buildings too. Now, let me go now to the second and most important, topic of today's talk, which is superinsulating materials. Now, when we look at insulating materials, we often tend to present that materials have, a non-thermal conductivity, 0.04 bond-meter Kelvin or in that range, and to insulate buildings more, we basically increase the thickness. However, a different strategies to work on materials that tend to nano approach have the possibility to reduce significantly the thermal conductivity from values that are in the range of 0.04 to values, as you can see on the right of this graph, that are in the range of 0.01 watt-meter Kelvin. Now, what is really the value of this is that you can get the same thermal resistance with a thickness that is a quarter of the thickness that you can otherwise have with a rock wool. And clearly, the value of this approach is that you save space. When you do a skyscraper with a material that is only thick, 1-2 centimeter, instead of material that is 10 centimeter, the general contractor tends to be quite happy, although the price is still a major challenge. So I've been working on aerogel, a very, I would say at this point, old material, because it's been really discovered 90 years ago. So it's not really a new material at all. It's basically made of, air at the end of the day. It's full of void. There's really that much material. It's 98% of void at the end of the day. But thanks to the extremely low density, typically in the range of few kilos per cubic meter, it is capable of getting a low thermal conductivity, an extremely low thermal conductivity. Now, this product, where it comes actually? It comes from the idea that if you have a void, as you can see on the left, imagine it is the cavity of a typical mineral wall, particles of air in that structure can move a lot. And that means that they are going to transfer a lot of it by convection significantly in porous material, such as mineral wall or fiberglass. But if you're capable of structuring a solid material like aerogel in a way that the particles of air doesn't have the possibility to move a lot and they never touch each other, then the heat transfer by convection really gets reduced a lot. And if you're capable also to put an opacifier in the structure of this gray bubble you see here, at the end of the day, even the radiation heat transfer gets reduced significantly. So in brief, aerogel do not really enhance conduction because the structure is like a pair chain. They don't really have convection because particles never touch each other. They never really move on significant space at the micro scale. and they don't have a lot of radiation because they put pacifier in the in the structure. So in brief, these are from a thermodynamics point of view, great ways to lower thermal conductivity of materials. Now we started this work 7-8 years ago by using already existing products, and we were working on creating new materials, plaster, boards, blankets, all materials that were really proving to be effective as thermal conductivity materials, highly insulating with very low thickness at the end of the day. But more recently, my group has been developing a unique and new kind of approach to produce aerogel. We wanted really to get over typical products that are expensive because they are patent, and we generated what we call a new innovative kind of aerogel blanket. Now, where this comes from is that the drying of the gel that is typically occurring in any aerogel, we do at ambient pressure instead of supercritical condition. Now, when you get what you often find in the market, supercritical drying processes, the price of all these products tend to be a bit higher, and we've been trying to lower the price of these products to really make them, faster in penetrating into the building industry without having an increasingly high cost. So I encourage you to look at this YouTube video to find more papers about the approach we've been following to get the ambient pressure drying processes. Now, just to give you the sense where we are right now, our products is not necessarily as effective as a few others, but the price is 5 times smaller. So our products tend to be in the range of thermal conductivity of 0.02. When you do ambient pressure drying, you don't really get rid of all the liquid portion, so you get a bit of a higher thermal conductivity. But then on the other side, these products that use supercritical condition, high pressure condition, and they need an autoclave, they really are hard to make actually the market and fight for becoming the dominant insulating material in the building industry, because producing this kind of material tend to be more expensive and only small sample size. We also have been working on a few other different aspects of aerogel products, things such as how do we attach an insulating product. If you have a super insulating product and you then attach it with material that are highly insulating, as we often see happening for insulating products, we get a lot of thermal bridges. So we have been also developing special glues with low thermal conductivity to attach these materials and low thermal bridge issues, as well as we've been working also with Alessandro, the chair of today's talk, to try to enhance the thermal conductivity, try to reduce the thermal conductivity, actually the thermal transmittance of windows, both in the frame part as well as actually in the window part. And here the work is both experimental as well as numerical. The idea is that which cavity really makes more sense to insulate with aerogel granulars, and what is really the beneficial impact of a frame with aerogel in the cavity. Now I'm going to move towards another insulating product, but it's not anymore aerogel, is low embodied carbon foams. Where this kind of interest comes is that foams in North America, for the air tightness request, it's a significant portion of the insulating industry. And the reality is that this industry has been affected by the importance and the critical role that CFC has played on the atmosphere and the ozone layers. So, after the Montreal Protocol, we started looking at alternative ways to get rid of the CFC because they were creating a lot of troubles. And we basically made sure that from using chlorofluorocarbon to have the expansion of the foam, we started using hydrochlorofluorocarbon. So HCFC are the blowing agent typically used in the second generation 15 years ago. Now, 10 years ago, more or less, in an effort to protect the environment, protect the ozone layer even more, we went through, a no ozone depleting gas at all. So we moved through hydrofluorocarbon, HFC, which are still the standard third generation blowing agent. And what we've been working on in my lab is just moving towards the fourth generation of blowing agents. So these are basically a blowing agent that have not only no ozone depleting power, but also a global warming potential of 1. Because at the end of the day, they use carbon dioxide to blow the foam. So the reality is that these kind of gases are, much more environmental friendly, But then on the other side, they have a bit of challenges, and we've been working on improving the challenges of these gases. Number one, the CO2 tends to escape from the material, and so air diffuses inside the material. And with air, a lot of water vapor enters into material. So moisture penetration is a problem. And when you get moisture penetration, the thermal conductivity is not anymore the nominal, kind of thermal conductivity, but it starts being, affecting the polymer structure. And really, this is what we call often as aging of the foam. The reality is that the polymer starts to degrade, and it occurs, a lot in the first month, but it will keep happening for the following years since the distillation. And the reality is that what we use it to have a thermal conductivity low, thanks to the possibility to cut as much as possible convection and conduction in the porosity of the foam, it starts being much more significant because here you start getting water vapor instead of the blowing agent. So what we've been working is the apparent thermal conductivity of these materials. And the apparent thermal conductivity, we're also working on the long-term apparent thermal conductivity. In other words, the material doesn't usually only conduct it, it does convection and radiation in the porosity. And we want to look at the long term to get the understanding of what the material will do, years after the application. So we have been working with, different techniques, different approach to look at the long-term properties of this material. There are some standards in North America that are helping us doing these kind of things. But in brief, what we've been doing is trying to overcome the assumptions that typically are done on heat flow measurements. We often, if you see the premises of most of the codes and standards and norms to look at thermal conductivity, you pretend the material is homogeneous, is no temperature sensitive, doesn't accumulate heat, doesn't get affected by airflow path, and more importantly, only transferred by conduction. In reality, these materials do quite the opposite. They are affected by air, they're affected by moisture, they're affected by temperature. So let me start looking at temperature influence. Now, as we can expect, higher temperature often means higher thermal conductivity. And that's a very basic, simple thermodynamics law. Higher temperature means more energy in the cavity. More energy means actually the particles are capable of moving more quickly. So faster particles movement really means higher thermal convection heat transfer. Now, more importantly, if you look at this graph, what you see is the results that are often coherent, like higher temperature, higher thermal conductivity for the yellow, the green, the orange, and the red. But then you start looking at this blue or even this brown, you start getting this strange scenario where at lower temperature, where typically the material should have less energy to start moving by convection, the thermal conductivity goes up. And it goes up by 50%. It doesn't go up by a little quantity. And you look at this and you start understanding the challenge of these products. The reality is that this kind of challenge are occurring often for polyisocyanates, by far the most common products these days in roofing for commercial application in North America. Polyurethane, the four top kind of graphs, do not necessarily have a significant impact, but polyisocyanates have a significant impact. Now, in this graph, you also find the results of material in dry condition or after being exposed for 24 hours at relative humidity level of 80, 90, and 95%. And you see there are materials that not really change that much their thermal conductivity, but they are materials that are capable of really, grabbing a lot of moisture and coming up with a thermal conductivity that's completely different from the nominal value. So in brief, what we've been working is trying to promote laws and approach where the thermal conductivity, instead of being a single value when it comes to these super insulating products with innovative foams and with innovative blowing agents, are 3D curves where thermal conductivity gets, as a parameter affected by relative humidity and temperature. And we've been doing this kind of modeling and studies where we've been looking at real field materials, putting sensor thermocouples and thermal heat flux, and looking how in winter, for example, you get very stable condition, and then on the other side you start getting significant challenge when you start getting lower temperature. You can see here the dotted line that represent the general result of the exterior surface of that same material, supposedly to act at 0.02 watt-meter Kelvin, ended up being at 0.06 watt-meter Kelvin. And you can expect this is really kind of challenging, especially if we want to promote high-performance buildings, because you look at hypotheses that are not reflecting in real field. We also have been working on trying to improve this polyurethane thanks to aerogel. So we've been doing some work and papers on aerogel blowing within the polyurethane component B. And that's it. So I'm gonna, in the interest of time, I'm gonna stop here just to give you a bit of panoramic. And before leaving you, I want to give you a bit of the sense of what are also we doing for novel technology and new materials. Now, first of all, we have been working on possible application of new materials for fighting Woolman Island effect. A significant problem, especially in Toronto. If you look at that kind of slide that I was showing you before, you really get the sense of how critical it is for a city that develops a lot to put a lot of those towers and getting a lot of thermal storage for materials that at the end of the day are going to store a lot of that solar radiation. So we have been working on kind of colors, different reflectivity, material with a kind of a traditional color in the visible range, but with a thermal reflectivity that is much lower or much higher to get actually promoting options for new construction in Toronto. And to be honest, this has been a very effective strategy of engaging with the government, because the government has been putting a lot of new incentives for people to look at cool materials. So right now in Toronto, there are significant financial benefits for those people using cool materials in their buildings. We've been working on reflective materials, so as a way to not only cool down your building, but also cool down the opposite building. So making sure that that kind of reflectivity of the material doesn't necessarily become an extra gain for the opposite building, but gets reflected back towards the sky. And that kind of reflectivity and retroreflectivity at the end of the day has been done for new materials, virgin material, and aged materials. So the skills that we have developed in testing aged materials have been often strategic for cool materials research, because we have been able to do research in terms of what happens to this material when they move forward, years after installation. Now, it's similar research not only for the opaque portion of the envelope, but also for the transparent portion of the envelope. It's been helping us in working on nano coatings for windows. The idea here is very simple. We are looking at material that only allow high visible transmittance in the visible range, and they're able to cut completely the solar infrared. We've been working with a company that has been partnering with us and patented a product that can be basically applied in post-retrofit of windows. So existing windows, they can coat it with this kind of material coating that really help us, cutting down significantly, as you can see from the graph, the transmittance of this material from a clear non-treated glass to a traditional low E treated, down to actually a clear treated material really goes down. And if you can combine, the lower infrared transmittance of this product with eventually a low E, you start getting, a window that really has the possibility to just allow visible light to pass through, and making sure that, whatever is not interested, really get transmitted a percentage of a few percentage point, both in the ultraviolet as well as in infrared range. And last but not least, we've been starting working a couple of years ago. Then the pandemic resulted in a bit of a delay in this kind of research line, and I've been spending more time outside Canada over the last couple of years. But we've been working on thermochromic materials and the possibility of these materials for the city of Toronto. So we have a new facility test, and we have been testing different tiles on model box and real field boxes, and we look forward to do a bit more research in this field. Now, in the interest of time, I would like to acknowledge all the research sponsors that have helped often financially to support all the fantastic students that made most of the work I've been able to describe to you. And that's it from me. I thank you for the invitation and look forward for any question or curiosity. Thanks so much.
Thank you, Umberto, for this inspiring presentation. I wonder if there are any questions. I just wanted to ask, in what percentage do these new technologies affect the cost of construction of buildings?
That's a good question, because I've been talking about so many different technologies that it's often hard not to say that the new technology, the more innovative they are, the less critical mass of production occurs. And so clearly the problem at the end of the day is not just a real construction, it's a construction model cost related issue. Because if nobody produces these kind of things and they're still under patent, at the end of the day, you start getting prices that have no sense from a real material manufacturing perspective, but they have actually a lot of sense from the rights protection perspective. Now, having said that, as you probably have appreciated through my presentation, I've been trying to work on materials that are more feasible. PCMs, tend to be expensive, and I've been trying to work on fatty oil and fatty acids that tend to be a waste for our sector. They can lower the price. Aerogel, you can look at supercritical drying aerogel. Fair enough, great material, super, performing. But I've been trying to push my students and my group to work more on ambient pressure drying, although it doesn't really behave as good as the supercritical drying. Will promise to have a low price at the end of the day. And so you can produce at at a significantly lower price. And this kind of approach has been clearly the trend. Now the reality is that I think one of the problems that I've been personally trying to address is to make sure that somebody uses these products. And so they familiarize with that and they ask your product, your advice when they have to solve a specific problem, like a specific thermal breach or a specific opportunity for something. I think that's really important because otherwise we do a lot of new material research and none of the construction people really know that kind of things. And I think actually this is the major issue we are facing when it comes actually to innovative building technologies, is that the reality is that the industry is conservative. They don't want to take risk. They don't want to actually, fail. And therefore, the reality is that we tend not to really go for new materials. And, it's understandable, and it's even more understandable in Toronto. Because imagine you have to fix a window, at the 80th floor, like 300 meters from the ground. I mean, clearly that you want to avoid that risk from happening. And to be honest, the speed of construction, and I was simplifying in the animation that I started the presentation with, really tells us that nobody wants to take any risk because the construction is just too fast. There is no time actually to test these kind of things, So price is a major challenge, to be honest with you. But on the other side, the goal for the building industry is, high. You are not going to do that kind of goal by incremental little change, by putting an extra inch of insulation every 3-4 years that you come out with a new building code. That's been basically the strategy we have been living in since 1973 crisis, That every new building code cycle, somebody was putting a bit of an extra request for R value, a bit of another insulation centimeter thickness, another actually little thing to help us. I think it's time that we realize that we need to do things, more drastic, more kind of important. And we need to do those kind of things at the end of the day because building will stand there for decades. So the reality is that, the building that we are aiming to, to help addressing a different performance are buildings that will overcome my life. And in Toronto, we get this unique opportunity for new construction, but in many places, the new construction rate is quite low. And so the retrofitting, rate is so small, like 2% in Europe on average, that if we don't do drastic things every single time we get the opportunity, we will wait 50 years at the 2% rate of, intervention on an existing building. That is just incrementally 50 years later when somebody will, remember that he needs to do something else again. And I think actually that's the real question, is that building live too long. It's not a smartphone and 1 year later you change again and, you have the time to go to make a mistake. The building that is built is there forever. And this is a big issue.
Okay, there are other questions. Giampiero Colangelo says congratulations for the presentation. That was very clear and interesting, and asks if there is any study on LCA on these materials.
No, good question. Well, it depends. Let me put in this way. I haven't seen any study on LCI, for example, comparing ambient pressure drying versus supercritical drying of aerogel, no? But the reality is that it will be, interesting that somebody does that kind of research. And more importantly, we can expect that the difference is significant, because if you need to reach a few thousand Pascal to dry a material, or you can do it at ambient pressure, like 1 atmosphere in a microwave, or doing ambient pressure drying, then you understand that the energy implication is significant. And I think the same occurs with a lot of other products I was discussing. So let me put it in this way. I haven't seen a lot of LCA. I suspect that sooner or later, once this material will start being more stable in the market, somebody will look at these kind of things. Because right now, material manufacturing optimization is not yet there. Like, we get new materials, but we don't necessarily get yet an optimized production process, no? And this clearly, will result in an LCA that is not necessarily in favor of this material. But at the end of the day, the reality is that I want to use more than my LCA approach, which, I know there are a lot of people looking at this kind of aspect of any material, any cycle, any product. I want to use my thermodynamic approach, not like, as you probably have seen, blowing gauge and aerogel, even thermal storage. At the end of the day, it's an heat transfer problem. And so far, we are working on the heat transfer problem. Sooner, we have to work on the environmental impact of these processes.
Okay. Dr. Siva Jagannathan asks if there is any possibility to do collaborative research work in this subject that you have done extensive research.
Oh yeah, for sure. Like, to be honest, basically a lot of the research you probably have actually heard today, it's a collaborative effort. No, I would have never imagined it, how to say, 10 years ago, that some of the publication will have been more on chemical related journals than on building related journals. And very similarly, I think actually a lot of the effects is only going to occur if people from around the world, with different contribution, try to align their vision. Like each one of us, at the end of the day, pushes a completely different material and a completely different approach, we may take a risk of losing opportunity. So I basically have been giving you, examples of aerogel, no? But these are not the only ones that are often categorized as super insulating material. They are the vacuum part. There are many other approaches, no? And so clearly we need to understand who is working effectively on these topics and try to come out as a group, no? At the end of the day. I got the impression that over COVID, I actually had, family-related circumstances that hasn't necessarily been allowing me to travel a lot. But, this is probably true for a lot of people under COVID. Over the last few years, there has been a significant reduction in collaborative effort. People tend to travel less. The situation in many countries doesn't yet allow these kind of things. And we are losing time. And we are losing time where we do the construction. We are losing time where the construction is happening. And so it's critically important that we try to collaborate more effectively. And in my opinion, we try to promote that, one building here, one building there, test and introduce one material, in their construction fabric. Because that really creates a bit of a confidence that the material can work.
Well, Kalim Allah thanks you for the explanation and invites you to explore novel objectives in this particular area of research, especially evolutionary algorithms like multi-objective optimization algorithms and so on. And you are also invited to speak about material and optimization, material manufacturing and optimization, which is another aspect of sustainable development assessment. And moreover, someone asks you to share your contacts, like email or other forms of contact to write you for more information.
Perfect. Yeah, no problem at all. It's easy, but yeah, I will make sure that.
Okay.
Yeah.
So, I think the Q&A session was quite rich, and I again ask you, thank you for being with us today and for sharing your research results and knowledge. And so thank you again.
Thanks
Umberto.
for inviting me.
Dr. Itra Ghosh is not with us today for important health reasons. Who is a lecturer at the University of Exeter. He had to talk us about smart and advanced type materials for windows and innovative buildings. And on the other hand, let me introduce the last speaker today for our webinar, who is Dr. George Syrrokostas, who is currently a research associate at the physics department of the University of Patras in Greece, where he also received his PhD degree. His current research is focused on the synthesis, characterization, and application of nanomaterials for third-generation solar cells, mainly dye-sensitized solar cells and perovskite solar cells. He also works on the development of novel photoelectrochromic devices for energy-efficient buildings. Well, George, the stage is yours. If you want, you can share your presentation.
Thank you. First of all, I would like to thank Dr. Cannavale for his kind invitation to present my work on photoelectrochromic devices in this webinar. This is the outline of my presentation. First of all, I will start with a short introduction about energy efficient buildings and the different technologies of smart windows. And then I will try to present you the topic of photoelectrochromic windows. As you may know, nearly 30% of our energy consumption is by buildings, and the major part of it is to cover our heating and cooling needs. At the same time, buildings exchange a large amount of heat with their surroundings through windows, which determine the thermal load of a building. Therefore, today there are different technologies of smart windows that can control the thermal load by altering the their optical properties. Among the different technologies of smart windows, we have the electrochromic windows. Electrochromic windows offer a dynamic control of their transmittance with the application of a DC voltage. That means that the user can control the amount of solar heat and visible light that enters inside the building. As a result, electrochromic windows offer cost savings up to 20%, but this percentage depends on the climate zone, on the control strategy, and a few other parameters. Here you can see also two pictures of an electrochromic window that was prepared in our laboratory in its bleached state and in its colored state. On the other hand, photoelectrochromic windows, that is the topic of my presentation, that don't need an external power supply in order to work, since they utilize solar energy. Their optical modulation is being automatically activated depending on the available irradiance and
George, excuse me, George.
Yes.
We cannot see the slides at the moment. We just see the first one. Probably you have to share the full screen of the presentation with us.
Okay.
Sorry
for that. Now?
Yes, now it's okay. Thank you.
Now it's okay. Okay. As I said, electrochromic windows are windows that one can control their transmittance with application of a DC voltage. And now you see the pictures I told before about the electrochromic window we have prepared in our lab in its bleached state and in its cold state. Photoelectrochromic windows they don't need an external power supply. They can utilize solar energy to work, and their optical modulation is being automatically activated by the available irradiance. There's no need for electrical power for bleaching them, and also the coloration kinetics are scale independent. So these photoelectrochromic windows have a dual behavior. On the one hand, they can generate energy, and on the other hand, deliver a smart optical response. Therefore, as we will see, they combine a PV unit with electrochromic unit in one unified device. The first appearance of photoelectrochromic windows was nearly 25 years ago in Nature, where a photoelectrochromic window with an active area of 25 square centimeters achieved an optical modulation of 20% in less than 2 minutes. The architecture of such a device was very similar to that of a dye-sensitized solar cell. In the case of a dye-sensitized solar cell, at the anode we have a nanostructured titanium film with thickness above 10 microns, sensitized with an appropriate dye. At the cathode we have a very thin platinum film, and between them there is a redox electrolyte like an iodide, triiodide 1. And the role here of the cathode is to collect electrons from the external circuit and to catalyze the reduction of triiodide ions to iodide. In the case of the photoelectrochromic window proposed in Nature, at the anode we have a very thin transparent titanium film sensitized by an appropriate dye. Again, since the film is very thin, the amount of dye molecules that can be absorbed on it are less. Therefore, the utilization of solar light is not so efficient. And moreover, at the cathode, the thin platinum film is missing, and we have the electrochromic layer. As a result, when photoelectrons are produced by the adsorption of dye, when they reach at the cathode through the external circuit, now they reduce the electrochromic layer, and due to the simultaneous intercalation of lithium ions, as we see here, the electrochromic layer changes its transmittance. Therefore, there are two key differences between the dye-sensitized solar cells and the photoelectrochromic windows. First, in the case of photoelectrochromic windows, all the components must be highly transparent. Therefore, the utilization of solar light is not so efficient. And also, the platinum film at the cathode is missing, meaning that the reduction of triiodide ions is not so efficient. And for both of these reasons, the photoconversion efficiency of these devices, at least initially, was negligible. Moreover, photoelectrochromic devices have captured the interest of many researchers around the world, especially the last 10 years. Here, in the last 10 years, we have 6 or 7 publications each year on this topic. And here in this graph, we see only research articles and not articles from reviews or from conference proceedings. Now, all these publications deal not only with the properties of the materials that can be used, or to explain the different mechanisms that affect the performance of the devices, but also deal with the device architecture. The device architecture is crucial since it can affect significantly the performance of the devices, and the challenge is to combine the PV unit and the electrochromic unit in one unified device. To do this, there are 3 different modes. In the first mode, we integrate the PV unit and the electrochromic unit into one single unit. These devices now have 2 electrodes. In the second mode, we use a common substrate. In this case, the substrate has its both sides conductive. This is a tandem configuration. And in the third mode, we connect the 2 units via a common electrode, meaning a common anode or a common anode and the devices now have a side-by-side configuration. Therefore, now we talk about multifunctional devices that, except from optical modulation charge storage as in plain electrochromic windows, also they can produce energy. An energy that is used not only for the optical modulation of the electrochromic unit, but also to power an external load. Of course, to power an external load, it's much more challenging. And I believe that with devices having a tandem configuration or a side-by-side configuration, this is more efficient. And here we see a timeline of the different device architectures that have been proposed the last 25 years. And to show you our contribution in the field, 10 years ago, we introduced the particle covered design. I will mention more later in my presentation. And also 2 years ago, we used the perovskite, a carbon-based perovskite solar cell to power the electrochromic unit of a photoelectrochromic window, having a side-by-side configuration. But to continue with the state art and the current state of photoelectrochromic windows, of course, there are different indicators to describe their performance. Here, I have chosen to show you two graphs. On the left side, there is a graph of the transmittance modulation in respect to the photoconversion efficiency of these devices. We see that today we have devices with photoconversion efficiency up to 14%, but in this case, the optical modulation is very low. Also, we see that we have many devices in this area, and also we have devices that have a photoconversion efficiency of 2 or 3%, but they have a transmittance modulation above 50%. That is comparable to a commercial electrochromic window that has been at least 50%. Of course, the challenge is to improve the photoconversion efficiency and having a transmittance modulation above 50%. And to do this, we need devices with having an initial transmittance above 70%, or at least in this area. And also we need to improve the coloration depth. To improve the coloration depth, it's much more challenging since we have electron losses. We have to cut the electron losses at the electrochromic layer electrolyte interface. This mechanism is called self-bleaching. There are different approaches for this self-bleaching. One is to deposit a barrier layer between the electrochromic layer and the electrolyte to prevent the direct contact of the redox electrolyte with the electrochromic layer. Other is to use different redox couples in order to have a higher charge transfer resistance on the interface and so on. Moreover, as I said previously, we care also about the charge storage properties of these devices. Indeed, in recent years, we have reports where the capacitance, where the aerial capacitance of these devices has been also measured. In the right graph, so we see the aerial capacitance of these devices in respect with their optical modulation. We see that we have significant values of aerial capacitance, but still the optical modulation is not above 50%. So if someone wants to improve the optical modulation, but keep the aerial capacitance at a logical level, can take ideas from the a field that is very close to electrochromic windows, photoelectrochromic windows, that is the energy storable devices, electrochromic energy storable devices, where in this case we have devices with optical modulation above 50%. In our case, in the case of photoelectrochromic windows, we have to examine the role of the redox electrolyte, its composition, and also how the different redox couples affect the charge storage properties of the devices. Therefore, we see that it's difficult at the same time to optimize the optical properties, the charge storage properties, and the solar energy harvesting. And here we can see some laboratory scale devices. Each of these devices have been carefully selected since they have the highest value of a specific performance indicator. For example, the area here has an active area that is the largest ever reported. We have a device with photoconversion efficiency around 14%, a device on the right side that has a very high aerial capacitance. Now, to continue my presentation, I will focus on our contribution in the field. When we started to work on photoelectrochromic devices, then there were these two different device architectures, the separated one and the fully covered one. Both of them had a very thin, transparent titanium film. Also, in the case of separated architecture, the electrochromic layer was at the cathode. In the case of fully covered architecture, the electrochromic layer was placed at the anode, and also we had the platinum film at the cathode. Both of them had its own advantages and disadvantages, but the common issue was the limited photoconversion efficiency. So we have proposed to use a very thick, non-transparent titanium film placed at one side of the device in order to improve the photoconversion efficiency. And here on the left bottom side of my presentation, you can see such a device with a non-transparent photovoltaic element that is placed now out of the optical path at one side of the device. We managed to, we achieved an optical modulation around 50% and in a few minutes, and the photoconversion efficiency that is still below 1%, but is higher than a device having a transparent titanium film, as we saw here in these JV curves. The device, our newly proposed device, has the JV curve as we show here, with a green line, and with a blue line is the device with a transparent titanium film. Also, the titanium film was covered a fraction of 20% of the total device area. Since then, we have examined a lot of parameters that can affect the performance of these devices. For example, the role of the electrolyte, its composition or its state. In this publication, we have used a polymer electrolyte membrane, and we show we achieved an optical modulation around 50% and the photoconversion efficiency of 0.3%. More importantly, the coloration time was less than 2 minutes now, and that shows that the diffusion of lithium ions inside the polymer electrolyte is very efficient, and also the faster coloration time is due to the improved value of the photoconversion efficiency. The most important now in this work was that here we can see photos of this device in different operation states. And the most important in this work was that we proved that such a device can be stable even after exposing the devices under real outdoor conditions. Here we see the transmittance values in their initial bleach state and in their colored state. We see that their values are very constant even after 90 days of continuous of exposing them under outdoor conditions. That was an aging test that was performed for the first time then, and I believe the only time until now, since the stability of these devices is examined usually using continuous cycling. Later, we have used an electrolyte having a copper-based redox couple to replace the iodide-triodide redox couple. In this case, we wanted to solve the corrosion problems that usually are met with the iodide-triodide redox couple. Also, we used a very thin graphene nano plate film instead of the platinum film. In this case, the optical modulation was above 60%, and the coloration time was very fast in only few seconds. Again, these devices were extremely stable even after 400 days of continuous operation. Also, 2 years ago, we used a carbon-based perovskite solar cell to power the electrochromic unit of a photoelectrochromic window having a side-by-side configuration. Here, the PV unit was covered only 4% of the total device area. That means that in the previous cases, the coverage fraction was 20% or 15%. And that means now that we have a less area of our device that is optically inactive. In this case, the transmittance modulation was around 40%. The photocorrelation efficiency reached 3% and so on. In this case, because the photovoltaic unit and the electrochromic unit are not combined, are not integrated, they can, I believe that they can, let's say, optimized separately, so there is ample room for improvement. Therefore, our idea for these devices is to have a very small photovoltaic unit that is placed at the one end or at the perimeter of the device, and this small unit to provide energy for powering the electrochromic unit. And our idea was followed later by other researchers, as we see here. And also we see that there are commercial products of solar-powered windows. Of course, there are here the PV unit is externally connected to the electrochromic unit. There is no sign of integration, but again, that we see that we have a photovoltaic unit that's placed at the bottom side of the window, or even inside the frame, and having very less area than the electrochromic one. And to conclude with my presentation, photoelectrochromic windows are solar-driven windows for energy-efficient buildings. They are truly multifunctional devices. During the last years, new materials and new device architectures have been emerged that promise significant improvement in their performance and stability. Coloration and bleaching can be in the range of few seconds, optical modulation even above 50%, and photoconversion efficiency depending on the device architecture. These all are the good points. On the other hand, there is limited knowledge about their thermal insulation properties and their true energy production ability. There are no systematic studies showing the dependence of their performance on light intensity, angle of incidence, or even shading. We have to improve their charge storage ability and, of course, open circuit memory through minimizing self-bleaching. We need more large area prototypes. And in my opinion, we have to set up specific performance indexes and testing procedures, because sometimes it's very difficult to compare the results between the different research groups. I would like to thank all of my collaborators and all of you for your attention.
Perfect. Thank you very much for this interesting presentation, George. And let me check if there are any questions from the attendees. At the moment, I have two anyway, so I start with mine. I just wanted to know what kind of techniques you generally use to prepare your tungsten oxide layers in photoelectrochromic devices, and if you have used any other electrochromic material in other devices? And what is, according to you, the expected cost of this technology in large area devices in comparison with ordinary glass?
Okay. First of all, we usually deposit tungsten oxide films using E-beam gun evaporation. Now we want to use other techniques such as salt gel and deep coating or spin coating, because if we want to improve the charge storage ability of these devices, we need to have an electrochromic film that is more porous or not so compact as we get with E-beam gun evaporation. But on the other hand, with E-beam gun evaporation, we have very uniform films that have a very high stability and uniform coloration. We haven't used yet other electrochromic materials except tungsten oxide. And about their cost, this is not easy to answer. I think that a commercial, let's say, electrochromic window is the cost of an electrochromic window is 2 or 3 times more than a double glazed window, if I'm not mistaken. So probably this technology will be much more expensive, and the only that we can do is to add more functionalities to our device in order to, let's say, rationalize the high cost.
Yes, I agree with you. Moreover, we have to say that there are a lot of benefits that derive from the use of these technologies in terms of visual comfort and reduction of energy uses for cooling in summer. And
Yes,
so on.
yes.
Thank you very much. It seems that there are no other questions at the moment. So probably I can thank you for being with us and for sharing your presentation. And just let me spend you just a few words more, because I want to thank the editors of the Building Journal, especially Mei Zhang for her precious support, and Jack today, as well as all the attendees of this webinar who have been with us. Furthermore, you are all invited to submit your manuscripts to for the special issue Novel Technologies for Energy Efficiency in Buildings. So you're all invited to submit your valuable manuscripts. And this special issue is guest edited in collaboration with Dr. Fabrizio Mariano and Dr. Marco Pugliese. Last but not least, I would like to thank all the invited speakers for sharing their precious knowledge with all of us, and just thank you all.
Thank you very much, Alessandro. So, as Alessandro mentioned, there is a special issue associated with today's webinar, which is in the chat. I'd like to remind everyone that certificates will be made available on your SciForum profiles. They should be made available by the end of Monday, and that the recording will be available in the coming weeks on the SciForum page. Thank you to everyone, our speakers, our attendees. I hope you have an amazing day, morning, evening, wherever you are in the world. Goodbye.